Hello, curious minds, and welcome back. Today, we're diving into one of the most essential ideas in mathematics, place value. This powerful concept is the very foundation for understanding how numbers work, whether you're dealing with a simple whole number or a complex decimal. Place value is like the secret code that helps us understand what each digit means in a number, right? It's super important for everything from adding and subtracting to tackling those tricky algebra problems. Think about it. In the number 345, the 3 isn't just a 3. It actually means 300. In this video, we're going to explore the fascinating world of place value together. We'll break down the basics, show you why it's so important, and give you real-life examples that make it all click. A key player in the story of place value is the number 0. Its importance really shines when we compare how it's used in different number systems, particularly the decimal system we use every day and the binary system that powers our digital world. In the decimal or base 10 system, 0 acts as a crucial placeholder. It's what gives other digits their correct value. Think about the number 406. That 0 in the middle is telling us there are no tens, which is a very different value from the number 46 in the binary or base 2 system, which is the fundamental language of all computing. The only digits that exist are 0 and 1. Here, 0 isn't just a placeholder. It's one of only 2 characters used to represent all information, with each position representing a power of 2. Let's look closer at the decimal system, which we also call the base 10 system. The role of 0 here is to be a placeholder, indicating the complete absence of a value in a specific position. It could be the ones, tens, hundreds, or any other place. This function is vital because, without 0, the place value of all the other digits would be thrown into chaos. For instance, as we saw, the number 406 has a completely different value than 46, all because that 0 is holding the tens place and showing there are no tens. Let's take a bigger number. Now, let's switch gears to the binary, or base 2 system. This system is the bedrock of all modern digital computing, and it operates using only 2 digits, 0 and 1. These digits are often called bits, which is short for binary digits. In this system, the role of 0 is just as fundamental as 1. The impact on place value is different but equally important. Instead of powers of 10, each position in a binary number represents a power of 2. You start from the rightmost digit, which represents 2 to the power of 0, which is 1. The next position to the left is 2 to the power of 1, which is 2, then 2 to the power of 2, which is 4, and so on. A 1 in a position means you add that power of 2, while a 0 means you don't. So, 0 is critical for constructing any and every number in the binary language that computers understand. So, let's formally define it. Place value is the term we use to describe a digit's value based entirely on its position or place within a number. In our everyday decimal or base 10 number system, every single spot corresponds to a power of 10. This means that for every position a digit moves to the left, its value increases by a factor of 10. Let's use the number 543 as a clear example. The digit 3 is in the rightmost spot, the unit's location, which simply denotes a value of 3. The digit 4 is in the tens position, which means it stands for 4 tenths or 40. And the digit 5 is in the hundreds position, so it represents 5 hundredths or 5 hundreds. Each digit's value is determined by where it sits. We can't talk about place value without highlighting the immense importance of 0 once more. The entire place value system truly relies on it. 0 serves as an essential stand-in, a placeholder, to show that a certain value is missing from a position. For example, in the number 506, the 0 is there specifically to tell us that there are no tens. If that 0 wasn't there, the number would simply be 56, which, as you can see, is a vastly different quantity from 506. 0 holds the place and maintains the correct value of the digits around it. Let's get systematic and break down the place value positions. First, We have the units place, also known as the ones place. In any number, this position is held by the rightmost digit. It shows exactly how many single ones are present in the number. For instance, if we look at the number 768, the digit 8 is in the units location, which tells us there are precisely 8 ones. Moving one spot to the left, we arrive at the tens place. This is the second digit from the right. It displays the number of groups of 10 that are present in the number. In our example of 768, the digit 6 is in the tens position. This means it doesn't just represent 6. It represents 6 groups of 10, or 60. The next spot to the left is the hundreds place, which is the third digit from the right. This position shows the number of groups of 100 that are in attendance. Taking our number 768 again, the digit 7 is located in the hundreds position. Therefore, the 7 represents 7 groups of 100, giving it a value of 700. When you put it all together, you have 700, 60, and 8, which combines to make 768. This pattern of increasing power doesn't just stop at the hundreds. It continues infinitely to the left as our numbers get larger. The fourth digit from the right is the thousands place, representing powers of 10 cubed. The fifth number from the right holds the 10,000s place, which is 10 to the fourth power. The sixth is the 100,000s place, and so on. There is absolutely no end to this pattern, allowing us to represent any number, no matter how gigantic. The rules of place value aren't just for whole numbers. They apply to decimal numbers as well. Decimals represent the fractions or the parts of whole numbers. The decimal point is the great divider. It separates the whole number part on the left from the fractional part on the right. Each place to the right of the decimal point symbolizes a negative power of 10 or a fraction. The first spot to the right is the tenths place, 1/10. The second is the hundredths place, 1/100. The third is the thousandths place, 1/1000. And this pattern also continues infinitely, allowing us to represent incredibly small values with precision. This might seem like just a classroom topic, but a solid understanding of place value is essential for many practical applications in our daily lives. To perform basic mathematical operations like addition, subtraction, multiplication, and division correctly, you must have a firm grasp of place value. It helps us comprehend very large values and evaluate the magnitude of different numbers at a glance. For instance, when you're adding or subtracting large numbers, it asks the alignment of integers according to their place values that ensures you get a precise and accurate result. The value of 0 is always 0, no matter where it shows up in a number. It's like magic, anything times 0 is still 0. While 0 itself doesn't carry value, it plays a super crucial role as a placeholder. Think about it. Take the number 101. Without that 0 hanging out in the tens place, it would just look like 11. How wild is that? It's like Zio is the unsung hero of numbers, keeping everything in its right spot. So next time you see a Zio, remember how important it really is. Furthermore, knowing place value and multiplication is a huge help, as it facilitates the division of large numbers into smaller, more manageable chunks, making complex calculations much simpler. Now, let's look at something interesting. We have a sequence that appears to be a list of numbers. -12, -9, -6, -3, 0, 3, 6, 9, 12, followed by a plus sign. At first glance, this might look like a mathematical expression or a sequence of integers. However, it's currently incomplete because that final plus sign doesn't have another number, or an operand, to complete the operation. As a result, the intended calculation cannot be determined without knowing what number should come after the plus sign. However, if we look at this purely as a sequence, a fascinating pattern emerges. A sequence is just an ordered list of numbers. In a previous section, we defined a sequence as an ordered list of numbers that follow a specific rule, and we chose to adopt that notation here. A simple example of a sequence is 3, 6, 9, 12, where you add 3 each time. Looking back at our list, It also follows a clear pattern. The absolute values decrease from 12 down to 0, and then they increase right back up to 12. More specifically, each number is generated by adding 3 to the previous one. This makes it an arithmetic sequence. And let me tell you, the number 12 is pretty special. Negative 12, or just plain 12, is that natural number that comes right after 11 and before 13. Cool, right? Mathematically, 12 is the third superior highly composite number, making it significant in number theory. In mathematics, many different types of sequences exist, and they are generally categorized by the specific rule or pattern that defines how each term relates to the next. The most common types are arithmetic and geometric sequences. Our sequence, -12, -9, -6, and so on, is a great example of an arithmetic sequence because each term is simply found by adding a constant value of +3 to the one before it. Thank you for watching. If you like, please like and share.